All right, well, good morning, everyone, and welcome to our last seminar in the series. Oh, here's Claire. She's very good. Yeah, so welcome to our last seminar of the series before we go into the summer. And Shobita and I would like to have your input as to how you would like to extend this seminar series into the summer. In terms of topics and format, frequency, et cetera, et cetera. If you have any opinions, any requests, we would love to hear that. We haven't quite planned how we're going to do it, so this is a good time to get your input. And for today, I'm very excited to introduce Anne Medling, who is with us. She is an assistant professor at the University of Toledo. And she graduated with her PhD from the University of California at Santa Cruz, where she was doing some awesome work on adaptive optics with Claire Max, who is here with us. And she was also an NSF fellow when she was a student at UCSC. And then after she graduated, she moved all the way to Australia, where she was a postdoctoral fellowship at ANU and worked with Lisa Cooley's group. And then after she did that, she came back to the US with a Hubble fellowship. And she worked at Caltech, where she had gotten her undergrad degree. And then she went, when she was at ANU, she was working with the SAMI team, the SAMI Galaxy Survey, which is an integral field spectrograph on the telescope at, what is it called? I forget the name of the telescope, but the 4-meter telescope. And then so she went from, deep observations with AO and IFS to go and link them with simulations with the Phil Hopkins group while she was at Caltech. And then I believe, if I'm correct, that she took her Hubble Fellowship to the University of Toledo to finish there. That's right. And then where she has been now, an assistant professor. So she's an expert in these techniques of integral field spectroscopy, as well as adaptive optics. I got to observe with her at Keck, maybe once or twice.
Very first Keck run.
Your very first one?
Yeah.
Awesome. And and now she also uses ALMA, which I'm very excited to hear about today. And so, Anne, thank you for coming and welcome.
Great. Thank you so much, Gabby, and everyone. I'm really excited to be here. I haven't been able to attend these regularly because I'm usually lecturing during this slot, but now it's finals week, so I'm happy to give one more lecture. And I really appreciate all of the archiving and video recordings that everyone has done. Reflecting on the seminar series as I was deciding how to frame my talk, and you've just had so many wonderful speakers and interesting things you've already talked about. So I'm going to try to hit a slightly different note, and we'll see where we go. So I want to start by expressing some gratitude first for the privilege of observing from Mauna Kea, or with telescopes on Mauna Kea. Of course, the cultural significance is such an important part of the island and of the mountain. And so I hope to share some of the wonder that I've gotten there with the science with you all. And of course, also from my many collaborators, a number of whom are here now, but I will highlight especially some of the work by my student, James Agostino. So, so with that, I wanna just give you a little bit of an intro. I took out like 10 intro slides because you all are experts, but I kept a few in just for completeness. So of course, we understand that our understanding of galaxies is that we generally start out rotation-dominated, disky, blue star-forming, gas-rich galaxies, and over cosmic time, these galaxies can move from the right of the screen towards the left as they sort of lose their ordered rotation, they run out of gas, they stop forming stars, their stellar populations age, and they end up sort of these red quiescent galaxies. And so An important thing is that gas really dominates this transition, or the reasons behind it, right? If you keep on funneling in new gas, you're going to keep on building up a disk. If you stop funneling in new gas, then the disk will dissipate over time. If you use up all your gas without replenishing it, then you're not going to be able to form very many new stars. Or there are a number of processes that can cause us to lose our gas, right? So this is feedback, which of course you all know all about. So looking at feedback from a simulations perspective, we can look at sort of the distribution of galaxy luminosities. So this red line here shows the expected number of galaxies at each luminosity, or as a function of luminosity, from our understanding of cold dark matter motivated theory, right? So we have this many dark matter halos of this many sizes, and if that correlated exactly to a reasonable amount of or a constant star formation efficiency, then we ought to have a distribution of galaxies with those luminosities, but we don't. So we can see that on the left side here, we have too few low mass galaxies, and we have too few high mass galaxies, right? High stellar mass galaxies. And so what simulators have found in the last decade or two is that if you add in star formation driven feedback, supernovae, et cetera, then you can really suppress the star formation in the low mass galaxies, but it is insufficient to bring those very high mass dark matter halos down to the lower luminosities that we see them at, unless you add AGN feedback, right? So it is stronger in these high mass galaxies, and it can really suppress the star formation on the high end. So of course, we also know that AGN feedback is important because we see evidence of it in extreme systems. So we see radio jets that stretch for hundreds of kiloparsecs. We see outrageously high velocity winds that can only be driven by something energetic like an AGN. Then we also know, of course, that the black hole mass and properties of the host galaxies are tightly correlated. So that suggests some kind of regulatory relationship. Maybe the black hole is able to regulate the growth of the galaxy, or maybe the other way around. Maybe the galaxy can sort of suppress or promote growth of the central black hole. Or maybe it's sort of coincidence, because if you bring in gas, you can form stars, you can also grow the black hole. And if you have no new material, then you're going to have a hard time growing either of them. Okay. And so initial simulations with AGN feedback easily quickly quenched galaxies during sort of this post-merger quasar mode feedback phase, right? So here we have some early simulations from 2005 with the black hole and without the black hole. So the top row shows different snapshots of this gas-rich merger when there's a black hole and AGN feedback turned on, and then the bottom row is without. So you can see here in the top row, as galaxies come in, they collide, and then this sort of bright quasar turns on this feedback, and it basically blows out the gas, and we're left with no cold gas in the final time step shown here. Whereas if you have no AGN feedback, then basically that cold gas remains gravitationally bound and is able to sort of come back and reform that disk. So in this era, people basically said, oh, AGN feedback can quench all of our galaxies, it can solve all of our woes, and we will just use that to explain all of galaxy evolution. So, since then, I think people have walked back that claim a certain amount, right? We think that it is important in some galaxies, in some circumstances. It probably plays an important role overall in galaxy evolution, but it probably doesn't solve every one of our questions. Okay, but with, I'd say the importance that simulations play in our understanding of AGN feedback and galaxy evolution, I want to sit down and sort of talk about what the important components are that go into an AGN feedback model. Because one of the things that we do is we say, okay, well, let's make this AGN feedback model and we'll test its predictions or compare them to our observations. But what goes into that, right? Those different prescriptions, the physical understanding of how things proceed. Okay, So that's where we're going today. So the first thing, of course, that is an important component of an AGN feedback model is the black hole accretion rate, right? So it almost doesn't matter what anything else is if you aren't able to understand how much mass is going into that black hole. That directly impacts how much mass energy is available for feedback. So what I'm showing you here in this plot is a graph from one of Phil Hopkins' papers in 2016 showing the inflow outflow rate for different subgrid prescriptions in each of these different lines, plus their sort of plenty resolved simulation that includes all of these things, right? So basically what you can see is that these different subgrid prescriptions that simulations often use differ by several orders of magnitude between each other. So a lot of our simulations pick one of these lines and goes with it, right? But you can see that they differ by quite a bit. So it matters which one you pick. And sort of the traditional Bondi-Hoyle accretion rate is actually like 7 to 10 orders of magnitude above this plot entirely. So, you know, don't pick that one. But in fact, most of our simulations use some Bondi-Hoyle related prescriptions. So nowadays, sort of modified Bondi-Hoyle is more common, but you can see even that is several orders of magnitude above some of the other ones. And of course, it surely depends on the situation of the galaxy, you know, the gas fraction or what the gas is doing. So what we've learned here basically is that it matters what you pick, and we need to be sure that we are choosing prescriptions that accurately describe how galaxies are and what sort of physics dominates there. Okay, so black hole accretion rate is important. The next thing is the feedback prescription, right? So some efficiency of the energy output based on the mass input, and also the timescales, right? So in simulations, a lot of things happen sort of between the time steps or, you know, below the spatial or temporal resolution limit. And so one of these issues that we've had in simulations, of course, is that the black hole is small and it's at the center. And so, you know, often simulations say, okay, well, once it reaches a certain radius, you know, our central pixel or our central resolution limit, I mean, say, okay, well, that particle has immediately accreted onto the black hole. And in doing so, then whatever feedback is associated with our feedback prescription is triggered. Okay. So we need to figure out if that is an appropriate assumption or if there's something else going on. Okay. And then the third sort of category of things is then what happens once you take that energy and dump it back out? Does it interact with the host galaxy? You know, how collimated is it? Does it heat a general area or sort of break out and reach the outer parts of the galaxy? How well does it couple to the interstellar medium and things like that? Okay, so these are the ideas that what we need to do is test and constrain observationally, right? Because simulators have lots of great ideas, you know, but it's up to observers to sort of figure out what is going on in real systems so we can then make these intelligent and educated assumptions. Okay, so now what I'm going to do is sort of reframe these out of sort of the simulator space and more into observer space, right? So we want to characterize what we can about mass inflow and mass outflow. So as far as mass inflow goes, we can ask questions like, what are conditions like near an accreting black hole? And when and how quickly do black holes grow? And if we want to look at mass outflow, we can ask questions about how collimated AGN-driven outflows are. We can look at the interstellar medium around them, ask questions like what volume of the ISM do these outflows heat or disrupt? And what is the multi-phase structure of the outflowing gas? Okay, questions so far? Okay, very good. Okay, so what I'm going to show you now, right? I'm sure most of you have seen this plot maybe many, many times, but this is just a schematic of sort of how the AGN or the black hole accretion rate or luminosity and star formation rate proceed over the course of a gas-rich merger, right? So the idea here is that in these early time steps, you have sort of baseline levels of star formation or black hole accretion. And then as we get closer to the merger stage, we get a bump, right? And that's because if you have a gas-rich system, the gravitational torques associated with this merger are able to sort of funnel the gas in towards the center, sort of help remove angular momentum from the system. So after first passage, then they might go back to a baseline, and then sort of around final coalescence, then you get sort of strong peaks where you get this starburst. This is sort of the LIRG phase in our local universe. You get sort of maybe a buried AGN as black holes start to accrete more and more, and then eventually they'll blow out. So any gas that hasn't been already forming stars or accreted onto the black hole might get sent far, far away. And then so far away that we really are ending up with much lower star formation rate or black hole accretion rates. And so that's sort of post-quasar phase into this post-starburst phase and towards the sort of boring old elliptical galaxy phase. Okay, so I'm telling you this because I'm going to come at today from sort of the framework that gas-rich mergers are a great place to study how star formation and black holes and their feedback affect galaxies. Of course, they're not the only way, but these are systems where we can look and say, I know that star formation is going on now. I know that there's plenty of fuel for the black hole, and I want to sort of understand the interplay between those things. Okay, so for that reason, I'm starting from a parent survey of GOLS, the Great Observatory All-Sky LIRG Survey, which is sort of the 200 nearby most infrared luminous galaxies, which in the local universe are almost all gas-rich merging galaxies at different merger stages. And so that means there's a lot of, or they're infrared bright because they have a lot of dust, which is heated by all of this extra energy from the star formation and from the AGN. Okay, so one really nice thing about GOLS galaxies is that they have this sort of tons of ancillary data from Spitzer, Hubble, Galax, Chandra, and many more, right? And now as JWST is coming online, these are a lot of the targets that we're going to see. Okay, so now I have sort of my target sample. Is that a question?
What content?
i.e. SGN.
So once we have our parent sample, then the next argument I want to make for you is that these systems are so complicated that what we want to do is go to the highest spatial resolutions that we can, right? And that's because I just argued that we're looking at star formation and AGN activity, and there's, of course, quite a bit going on. And so if we want to figure out, which outflows come from which parts of the galaxy, or, where how much of the ISM is being disrupted, or how much gas is available to the black holes, we want to go as close as possible. All right, so I mentioned there's Hubble data. So this is an example of NGC 6240, a galaxy that I'm sure you'll be more familiar with by the end of this talk if you aren't already. But essentially the idea is that if you go to the highest resolutions of Hubble, you can see two nuclei, sort of here and here, and each one of those has its own buried AGN. But you can't tell that from the Hubble data. And so when we go to longer wavelengths and with adaptive optics with Keck, you can see we actually get even better spatial resolution. So this north black hole, which is about here, pops up from behind the dust. The south black hole, which is about here, is not even completely unobscured at K-band, but is becoming more so. Okay. And so a quick overview of adaptive optics for those of you who aren't already converts. This is a sort of aftermarket observing system that we've introduced to many of our ground-based telescopes because everything from the ground suffers from turbulence in the Earth's atmosphere that just blurs and blurs and blurs. So this is that seeing limit that we are all familiar with. And so the idea is that if we can measure what those distortions are, then we are able to correct for them. So in this sort of optical schematic here, our light from the telescope is coming down with this distorted wavefront from the turbulence in the atmosphere. And if we can bounce it off of a mirror that's deformed in just the right way to counteract those deformations, then you can end up with a perfectly corrected wavefront. And so, of course, stars twinkle because that turbulence is changing all the time. And so what we have to do is measure it constantly and continue to update the deformations in our mirror. Okay, but if we can do that, then we win a lot, right? We gain because we have much better spatial resolution. And then we also gain because instead of throwing away a bunch of our photons below the noise limit out in the wings, we're able to sort of improve our sensitivity because all those photons that were lost are now found and piled up. So here's just an example of a seeing limited system. And then when you turn on adaptive optics, you see this bright target here with its strong flux profile. Faint companion is even visible in this case. Okay, and one more argument for adaptive optics. This is a picture of the galactic center in K-band. So with adaptive optics off and then on. And so you can see that, just as I said, right, so we're no longer confusion limited here because we can shrink the size of all of those stars. And then also stars that were way too faint for us to see in our blurry image are now able to collect all of their photons and peak up above the noise. Okay. So adaptive optics is wonderful for spatial resolution, but it's also convenient because we need to go to the near infrared because of that dust that I was talking about, right? So these gas-rich mergers have a lot of gas in the center, which means they naturally have a lot of dust in the center. And then of course the dust obscures our line of sight. So we'd really have a hard time seeing much of anything in the nucleus if we aren't able to go to longer wavelengths. Okay, conveniently, that's where adaptive optics operates. Okay, and one more advertisement for an observing technique. So integral field spectroscopy, for those of you who aren't familiar with it, is the data set where instead of having an image or a spectrum, you can't decide and you need both. And so basically you end up with a cube. So it's an image where every pixel itself is a spectrum. And so that means anything that you could do with an individual spectrum, you can now do spatially mapped across the face of a galaxy or across the nucleus or comparing different spatial regions. Very handy. Okay, so let me introduce to you a subset of the goals survey, the KOALA goals survey, the Keck OSIRIS AO LIRG analysis survey with myself and Vivian Yu as leads. Basically, this is the collection of OSIRIS data that we have taken over a very long time in both of our theses and since then as well. And so basically the idea is we want to look at the nuclear regions of these gas-rich mergers to understand a variety of things that are going on there. So by now we have well over 30 nuclei of these systems. And you can see from this sort of rogues gallery of a few that some of them are clumpy and some of them are smooth. And basically without this integral field spectroscopy, we'd never be able to tell you why. So some of them, like this one, are clumpy because they have lots of different star forming knots. Some of them are clumpy because they have multiple nuclei. So being able to look at the spectra and the kinematics around these different clumps tells us what it is. Okay, and so most of what I'm going to show you in the next few minutes comes from the K-band. So just for those of you who don't look at K-band, we have stellar absorption features from massive stars, and we have warm molecular hydrogen showing shock excited gas, and we have star formation indicators like bracket gamma, all in one filter. Okay, so let's see if we can use these data to look at some of these ideas we were testing and constraining observationally, so particularly mass inflow. So the first thing that we noticed is that nuclear disks in these galaxies are nearly ubiquitous, right? So as much as the overall kinematics of these galaxies is a complete train wreck, When you look close to the black holes, the dynamical timescales are shorter, and so they've had time to settle into these nuclear disks, right? So they're sort of puffy, turbulent, but still quite a bit diskier than otherwise. And they're multi-phase. We see them in ionized gas, we see them in that warm molecular hydrogen, we see them in young stars, and others have seen them in even cold molecular gas. So what's interesting is that these young stars are young enough that literally star formation is going on during the merger in these disks, right? So it's not that, these are concentrated nuclear star formation. Now, what's interesting is if you look at simulations, turbulent disks like this are probably pretty good at funneling gas efficiently down. So of course, with our data that I'm showing here, our spatial resolutions are sort of on the few tens of parsec scales. And so we know that the disks extend sort of down to that and sort of out to a few tens or hundreds of parsecs in size. But we know from simulations is that if you have a turbulent disk at 20 parsecs, probably you have a turbulent disk at 1 parsec, probably below that. And so gas, we expect, is funneling down. So this is naturally a great way to fuel AGN. Now, what's interesting, though, is to remember that Bondi-Hoyle prescriptions for black hole accretion assume that gas has no angular momentum. Completely no angular momentum, right? And what we're seeing in these systems is that gas has a lot of angular momentum. So that's probably a little bit of a concern, right? And we aren't the only ones to see this. A paper from Aaron Hicks in 2013 shows that if you look at, these aren't merging galaxies, but if you compare Seyfert's and quiescent galaxies matched in a variety of parameters, the Seyfert galaxies have higher V over sigma in the central few hundred parsecs, right? So that just sort of confirms this idea we have from simulations that those disky kinematics are probably helpful in fueling an AGN. Okay, so what did we learn about mass inflow? Well, the first thing we learned is that conditions near an accreting black hole are probably disky, and maybe Bondi-Hoyle accretion is not the best prescription for us to use. Okay, so the next question I want to pose is what we can understand from black hole growth timescales. Okay, so this is an interesting sample to look at because we know that black holes grow during gas-rich mergers, right? Because the galaxies grow, and we expect that before the merger and after the merger, they will end up on these scaling relations, right? Because they'll just be regular galaxies. But you might want to ask, well, how do they proceed over the course of the merger? Do the galaxy and the black hole just grow together in lockstep? Does the black hole grow early and then the galaxies mass growth catch up? Or is it the opposite, where the bulge of the galaxy grows first, you're forming stars, and then sort of towards the end of that, you're able to fuel the AGN, and let's say a quasar mode feedback event shuts off star formation and the galaxy bumps up. Okay, so what we would like to do is to measure black hole masses for these systems and put them on these scaling relations. But that's very tricky because of all the things I've told you before, right? These are unrelaxed systems. We can't use 3-interval orbital modeling, and there's a ton of dust in the nucleus, so it's too obscured. We can't use things like reverberation mapping. So what do we want? Well, we want a dynamical mass measurement inside the sphere of influence in order to measure that black hole mass. Okay, and so the convenient thing is I've also already told you that there are disks in the centers of these galaxies, and disks are relatively easy to understand, so we can model them to measure the mass profile inside. So I'm going to show you, I'm going to just skip over a lot of this so we can get to the punchline, but we have two different black hole mass measurement techniques basically to provide bracketing observation or bracketing limits. So the first limit is just to assume that velocity dispersion is not important. This is just thin Keplerian disk. We get a lower limit on the enclosed mass of these black holes. Then we can use Jean's axisymmetric mass modeling that does incorporate the velocity dispersion, which gives us an upper limit. And we can see that basically this gives us, in this particular case, which is the south nucleus of NGC 6240 again, we get an upper limit and a lower limit that are just off by a factor of a few. So we feel relatively confident that by modeling these kinematics, we can get a reasonable handle on that central enclosed mass. Okay, so we've done this for a bunch of different galaxies too. And what we want to do, remember, is figure out where these gas-rich mergers fall on black hole scaling relations. And what we want to do is try to interpret that information to learn about black hole growth and host galaxy coevolution. Okay, so you may have guessed when I described these arrows that sort of what we were expecting here is to find all of these galaxies below scaling relations, right? Because we expect canonically that quasars happen at the end of mergers, and quasars are that big burst to black hole accretion, right? Black hole growth. So we would expect basically them to follow this green line so we can jump up when the quasar turns on to recover our place on scaling relations. But that is the opposite of what we see. Right. Instead, all of our black holes are on or above scaling relations. All right, which is a little bit concerning, you might think. Well, wait, how is it that we have overmassive black holes? Now, what's interesting is just this week, there's a new paper by Duncan Farah looking at LIRGs at redshift of about 0.3. And you can see that also they see overmassive black holes relative to scaling relations. So at least it's not just us. But how does this align with our expectation that these mergers are going to turn into AGN soon, and they haven't yet, right? Because if they're already above scaling relations, are they just going to jump far, far, far above scaling relations? And what would we think would happen next? So if we can understand what's going on and why these appear to be above scaling relations and how that meshes with what we expect to happen next, that can tell us a lot about black hole growth. And just another note, we see overmassive black holes in all sorts of places, including these high Z quasars, right, which we'll never be able to get quite as detailed measurements of as we can look at this. So maybe this will give us clues to what we're seeing at very high redshift as well. Okay, so taking everything together and what we know, we feel like gas-rich mergers are more likely to have not necessarily overmassive black holes, but perhaps below our spatial resolution limit, there's quite a bit of mass, but that mass isn't all on the black hole yet, right? So imagine that this gas is funneling in, and it's funneling in, and it's hanging out near the black hole waiting to get there, right? We're still gonna measure it as a central dynamical point source mass. And if the distribution, the mass profile of this gas disk is not smooth all the way down, then we won't be able to know how much there is to correct for it. So basically what we are predicting is that there's sort of a pileup of molecular gas inside the central few tens of parsecs of these systems, and that mass is eventually going to enter and start instigating that quasar and its subsequent feedback, or maybe it's going to be some of the fuel that's going to get ejected in massive molecular outflows, which we think could happen. So maybe the dynamical mass will eventually lower. Okay, but suffice to say, we're predicting excess molecular gas, and anytime someone tells you that they're predicting something, you should say, well, how do you plan to test that? And so that enters the second part of my talk, this ALMA data, right? So of course, ALMA is a fantastically important tool for understanding molecular gas. And one of the key features it has is really high spatial resolution. And so if we look at the longest baseline data, we can actually match the spatial resolution that we're getting from our OSIRIS adaptive optics data. So this is the first data set at such high resolution. This is also NGC 6240 for consistency. So I have here on the left, right, that K-band image from Keck of these two nuclei. And then here on the right is that ultra high resolution ALMA data. So the colors are the CO2 to 1 molecular gas, and then the white contours show the continuum. So you can see that the continuum around these black holes confirms the presence of two black holes. And then in this galaxy, even though there is a bunch of CO around those around those nuclei, there's also quite a bit between them. Okay, so there are a bunch of papers out now thinking about or understanding what's going on with the molecular gas between these nuclei, but I'm not going to talk about that all today, because what we really want to know is, can we test our prediction that there's a lot of gas mass between or below our OSIRIS resolution limit in order to correct our black hole mass measurements. Okay, so I'm showing you here the enclosed continuum flux and the enclosed CO2 to 1 flux inside that resolution limit. What I'm going to do is try to use both of these to independently measure how much mass there is in that resolution limit. So for the continuum, what we're going to do is basically exploit the fact that the continuum comes from hot dust, and dust correlates with gas, and so then you can measure a gas mass under certain assumptions. And the CO, we're going to use an alpha CO measurement. So of course, many of you might know that there's a lot of arguments about what the proper alpha CO is to use in different systems. For us, we're lucky to have one that's calibrated, spatially resolved by Claudia Ciccone's high resolution data of this same system. So when we apply both of these, we basically find that there is quite a lot of mass in that spatial resolution limit. Okay, so here is the north and south black holes of 6240 with our old measurements. Right, this is just the total enclosed mass in the center. And then if I use these two different measurements of the gas mass and correct for them, then we end up with these more solid colored points. So you can see there's not very much gas in the north nucleus, but there's quite a bit in the south nucleus. And I might have time to say a few words about the discrepancy between the CO and the continuum. But you can see that, especially if you look at the combined north and south black holes, as they will be once the merger is complete, it's definitely sufficient to bring this galaxy back on scaling relations. Right, and so that very significant correction is something that we all ought to be concerned about if we're looking at black hole masses. Okay, so that was our first ALMA data, but since then we have equivalently high spatial resolution data of 2 more systems. So I'm showing you them here. So now the colors are CO as well, and then the contours are the continuum. And so you can see there's quite a bit of continuum and CO in the central regions of these 2 galaxies. Okay, so this is work that James has been working on. So his preliminary numbers for how much mass there is again quite significant. And so you can see it turns out in some of these systems, if you are measuring how much implied from the CO, it seems like it is also less than that implied from the continuum. And so we're still working on deciding exactly what assumptions we need to make about dust temperature and things like that. But certainly, depending on that, you can attribute a large amount of the dynamical mass to molecular gas in these systems. Okay, so is it ridiculous to say that there's a few times 10 to the 8 solar masses worth of molecular gas in the central few tens of parsecs? Maybe, maybe not, right? So R220 may have the same amount. Their molecular gas can dominate central dynamical mass in a number of Sieverts, as other ALMA groups have found. And simulations also have shown in some cases that the cold gas in the few central parsecs and tens of parsecs can be really dynamically significant. Okay, so, but on the other hand, there are other examples of high-res ALMA data that show no central molecular over density in those galaxies. But I'll point out that those particular galaxies are not AGN. So maybe this is telling us the difference about how and when we can fuel AGN and when they're in a quiescent state. Okay, and then lastly, I want to point out that even as far back as 2007, Rick Davies looked at a bunch of Seyfert galaxies and pointed out that they all have nuclear starbursts of a certain age, sort of 50 to 100 million years. So in that paper, they posited that maybe that means when gas comes into the center, it's available for star forming long before it's available to accrete directly onto the black hole or to turn on that Seifert. So is that kind of delay 100 million years or maybe more based on our merger timescales? Is that reasonable? And if you look at some simulations for different accretion timescales, one of the most interesting ones I remember from my grad school days was by Chris Power et al. Looking at sort of a viscous accretion timescale, right? So the idea is that they said, okay, well, it takes a certain amount of time for gas to lose angular momentum when there's viscosity and turbulence in this disk. And so if we delay, basically assign a time delay between entering the accretion disk and exiting the accretion disk to produce feedback, then it has really dramatic implications. And so depending on the parameters of your disk, that can be hundreds of millions of years time delay. Okay, so what we're learning is that there's lots of mass in the central sort of few tens of parsecs, and it's fuel for the AGN, or it could even be blown out in a molecular outflow. So we're hoping for more ALMA data in cycle 9. Okay, so we are looking at mass inflow, reviewing these questions we have. What we've learned is that near an accreting black hole, the gas is disky. It's not well described by Bondi-Hoyle accretion, and there's likely some delay between mass inflow and AGN activity. Okay, so I did not leave half the talk to talk about feedback because I think that you've heard a lot about this in other talks, but I just want to briefly sort of review some of the evidence and thoughts we have about mass outflow and AGN-driven outflows, right? So our integral field spectroscopy data provides spatially resolved mapping of outflows. So you heard this a couple of weeks ago from Vivian Yu. And so, of course, that's using a lot of the same data that we have, right? So we've seen evidence of AGN-driven outflows and star formation rate driven outflows, star formation driven outflows. And basically, we can look at how much shocked molecular gas there is, which can correlate with outflows, right? And so this is very analogous to optical shock diagnostics, which in sort of optical surveys we use as a as a proxy for identifying outflows, right? Because they these shocked line ratios correlate well with velocity dispersion. So it's basically as you would expect by injecting energy and turbulence into the gas, then it becomes more turbulent, higher velocity dispersion, but then these shocks increase the line ratios as well. Okay, so I'll probably skip talking about this case, but it's an example from one of our KOALA galaxies of a late stage merger, a very late stage merger, where we see this nuclear outflow on small scales. And then when we combine that with large scale, seeing limited optical integral field spectroscopy, we can see that the shocked gas extends above and below on large scales too, right? So that's important because when we see nuclear outflows, you don't a priori know whether it really has an impact on the host galaxy itself. So with this, we see that there's an ionized component and a warm molecular gas component. And if you check the literature, you'll see that there's also a definitive cold molecular component in these, in this particular galaxy, right? And they all are aligned geometrically with the same north-south. Okay, so the reason why I'm talking about this is because looking at the multi-phase structure of outflows is a really key constraint for observations to make for simulators, right? And so I'm showing you here one of these fire merger simulations along with the outflowing gas on the right. So this is a phase plot. So we have density on the horizontal axis and temperature on the vertical axis. You can see that in some time steps, we have quite a bit of hot gas that's outflowing, but then in some time steps, we see a lot of outflowing cold molecular gas, right? So pulling out just one of the key time steps, right, we can see this cold molecular gas outflow here in the black box, which is what we can probe with ALMA, and then sort of this ionized to warm molecular gas that we can probe with our ALMA data as well. And so understanding this phase structure is a really key constraint to give to simulators. But it's tricky because the way we measure things really depends on everything. So I'm just showing you this one spectrum from the galaxy Rs 17207. So there's two nuclei here in the center, and we have that outflow with the shocked molecular hydrogen. You can see that it's blue shifted. And this is an outflow that has been observed in many different transitions by many different authors. And so the scary thing is that if you look at the molecular and neutral and ionized gas velocities, you would have expected some sort of consistency where the ionized gas might be moving faster than the neutral or molecular gas, but it does not appear to be so, basically because the way we calculate our outflow velocities depends on a million different things, right? How we do our analysis, how we define an outflow velocity, what spatial resolution we have, what optical depth we're probing, and how far does that extend in the outflow. So it's really scary to think about that, but what we need to do is to be more careful about all of these. So the good news is that everyone's looking at AGN-driven outflows with data sets like integral field spectroscopy. So I just sort of throw a bunch of these up here: CARS, KONA, KOALA, AGN-IFS, S7, SAMI, MANGA, etc. And many of you here in this room are working on that, right? So that's great. So what that tells us is, you know, even though all of the answers to these questions about mass outflow seem variable in small samples, we can look at this data, and if we try to look at it carefully and consistently to answer these questions across a large sample, then I think we'll be able to make large gains. Okay, so just to summarize, we have new high spatial resolution multi-phase spatial and kinematic data sets that tell us things like we need to carefully choose our black hole accretion rate prescriptions. There might be a long time delay for mass to move from a few tens of parsecs down through to the accretion disk, and that can really impact how we understand AGN feedback to proceed, and that outflows are multi-phase. And so what we need to do is study the detailed structure, but it's now in reach. So if anyone is interested in using any of our KOALA data, please get in touch. We will be posting it eventually someday on our GitHub page, but if you're interested before then, just reach out. So thanks very much. I'm happy to take questions.
Thank you, Anne. That was a great talk. And as advertised from a different perspective, so thank you. Questions? Yeah, Giacomo.
Hi, Anne. It's Giacomo Venturi. Nice talk.
Thank you.
I have curiosity. So when you spoke about the fact that you observe a higher velocity over sigma in AGN rather than in normal or quiescent galaxies, that can be associated with the fact that you're funneling towards the black hole material through these disks, these circumnuclear disks, right? So I was thinking about the fact that the gas is often funneled through galactic bars, so towards the center. So I was wondering if you see any trace or signature of galactic bars in the shapes of these rotation curves, any warps, or any kinematic indication of bars.
That's a great question. And I have to say, so this particular work actually was not done by me, but done by Aaron Hicks and Matt Malkin and their collaborators. So if any of them are here, I welcome them to chime in. But I think that they're controlling for bars, no bars in this case. But someone correct me if I'm wrong.
Thanks.
I can speak quickly to that if you'd like, Anne.
Yeah, sure.
So I think I'd have to look back at the exact galaxies in the sample, but we did account, as Anne suggested, account for bars. And I'll say that we do see cases where there's clear large scale bars, and then that's funneling in with nuclear bars as well. So we see a lot of that kinematic structures on large scales, but then also on the scales that we're looking at here, hundreds of parsecs. So there is definitely inflow driven by those bar structures. In this case, where we were comparing the AGN and non-AGN, we did account for that, but it is a small sample. So everything's, small scale statistics here. Building up to larger samples would really be able to track that down.
Great, thanks.
All right, Sandra, and then Claire.
Hi, great talk. Thank you. I have a question about your ALMA data. I was wondering if the data is suitable to get the black hole mass directly from the molecular gas dynamics, or if it's too turbulent.
Great question. Let me just pull up. So, so I would say, so that was part of our original goal with NGC 6240, and in that galaxy, we don't see the gas in the cold molecular gas in rotation, which is so weird because we see young stars in rotation about these nuclei, and so it has to have been very recent that the cold molecular gas isn't there anymore, or maybe it's just that there's just much more of it between them that it's brighter, and so we couldn't see it. So we could not do it for 6240. Now, in our next two galaxies, we do actually see the gas in a rotation around the disk, or the cold molecular gas, the CO does show a disk, and so we are going to try, but we haven't done it yet. So, yeah.
Okay, that's great. Thank you.
Mm-hmm.
Claire.
Great talk, Anna. I really enjoyed it.
Thanks,
you have such good SAMI data, and now there's MUSE and KCWI also seeing limited IFU data. Have you tried matching up the large scale outflows that they see with the itty bitty outflows that you guys can see, or that we can see?
That's a great question. So no, not really, because they mostly don't include LIRGs in those samples, right? So there may be a few. I haven't double checked with MANGA's final target list actually, but in general, these big local smashing on the sky, don't quite line up with those highly multiplexed surveys. But we do have, so there's a number of galaxies for which we've gone and gotten targeted seeing limited. So the stuff I skipped over mostly, which I sort of alluded to here. Let me pull it back up. Right, so this is integral field spectroscopy from WIFES, which is on a 2.3 meter telescope in Australia, right? But it's a 2-armed optical integral field spectrograph, which is really, really fantastic instrument. But I basically have, I don't know, maybe like a dozen galaxies data just sitting on a hard drive waiting for a student to come help me dig that out, sort of targeting our same KOALA galaxies. And actually, I know collaborators have been looking at, so Vivian, of course, has been looking at getting some data for KCWI. She's a student working on that. We were using CWI on Palomar to do the same kind of thing as well. So sort of, I think one of Vivian's new postdocs is sort of angling to look at that. So hopefully in the next year or two, we'll have some really good insight.
Shobita?
I think Janelle was raising her hand, so I want to make sure.
Oh yeah, actually my question I was going to ask about black hole masses from the ALMA data too, because I'm definitely interested in hearing about that. But yeah, that was my question.
Okay, I would have imagined that would be a question you would ask, but Excellent talk, and that was just amazing data and really nice results. So my question is just to get us in the mood for what's next, which is JWST. And I know there are quite a few team members here. Vivian and Erin is here. So do you want to say a few words about the ERS program and the I think it's 4 targets, right, in that program?
Yeah,
What they've
so
chosen and the main goals, or what you're most excited about?
thanks. Yeah, so as Shovina mentioned, so I'm part of the JWST ERS survey, and so that's designed to pick. So we picked 4 of these ULIRGs or LIRGs and ULIRGs from the goal survey to look at, basically to try to do, the whole shebang of cool JWST things, mostly with the integral field spectroscopy, both with in the near infrared and now to the mid infrared. And so our sample of 4 galaxies spans a range of sort of like more traditional AGN dominated versus more starbursty dominated. But I think what's really interesting also, so of course the ERS data are really cool because they'll be available instantly and done hopefully soon, but we were a little bit constrained in our target selection because the instrument teams with their guaranteed time observations claimed a bunch of the really interesting, some of the other really interesting sources from our target list. So what that means is that over time, once that data all become public, we have like a huge selection of these interesting gas-rich mergers nearby that we will have tons of JWST data for, right? So that's going to give us sort of better insight into, through the dust, looking into the nuclear regions, and all that sort of thing. So it's really excellent for outflows and looking at the sort of the larger picture of things. I will sort of plug for Keck adaptive optics that in the near infrared, we are better resolved than JWST will be. Sort of our integral field spectroscopy pixels on JWST are going to be 100 milliarc seconds in scale, which is the coarsest scale that OSIRIS offers. But so maybe not that helpful for the local black hole mass sort of probing, but certainly for getting sort of the larger picture of the system, and absolutely for looking through more of the dust and getting some of those mid-infrared signpost markers. There are, you can characterize the phase structure of the gas much better when you have near infrared and mid-infrared H2 lines. And so I think that's one of the most interesting things I'm hoping to get out of our web data.
Great, thank you. And I do have a question, but I want to, it's the end of the hour. So I just want to ask everyone to thank you again. And then I'll ask you a quick question. So thank you.
Thanks, everyone. And feel free to email me if you have more questions.
So if you have a minute, my question is regarding that gas that goes into the central tens of parsecs. Mm-hmm. So you measure the molecular gas, and my question is, how much of that do you expect to stay in molecular phase? So I'm wondering if the fire simulations have that kind of resolution. I think the answer is no, right?
So some of their more detailed, well, okay, so it's a little bit tricky with the fire simulations because like only they haven't really implemented AGN feedback into them. And that means that even if they can make predictions, like you might not expect them to reflect what we see in real systems where there is an AGN or maybe an AGN soon. So, no, some of their latest simulations do have that really certainly higher resolution than our observations are probing. And so, we'll see what that has to say. But one other interesting thing that my student James is working on is looking at, not just CO2 to 1, but CO1 to 0, CO3 to 2, sort of at matched spatial resolution, so we can look at the temperature structure of the gas, because you do probably expect, so let's see if I don't know that you can see it in this image that I have. here. But if you look at this in a stepping through velocity space, you can actually see that there's sort of like a hole near the center in this galaxy of the CO2 to 1 flux. And so that, of course, makes me wonder, well, why is there a hole in the middle? You know, we were expecting more gas in the center, not less. And so that could be because there's no molecular gas, it's been dissociated completely, or it could be that it's, you know, moved up to a higher transition that we aren't probing with CO2 to 1. So that's what we're hoping to answer with his looking at the few different transitions. And work with so Loreto Barco Munoz is also looking at sort of the more full CO sled up to even higher transitions, but that has to be at coarser spatial resolutions.
Great. Yeah, that's what I was wondering about, you know, if you get ionized gas or even just atomic gas at the very center. So the masses that you're measuring are probably lower limits, and it's likely to bring the black hole masses even lower.
Could be.
Could be. Right. Great. Thank you. All right. Are there any other quick questions before we go? All right. Well, thank you so much, Anne.
All right. Thank you, everyone.